In unit number 6, we're going to focus on graph sketching. Now we need to have quite a lot of information at our fingertips in order to do this. You must know how to find a y-intercept. You must be able to find a stationary point and know whether it's a local maximum or a local minimum stationary point. You must also be able to find your point of inflection by looking at your concavity. Is your graph concave up or concave down? And then lastly, you must also be able to find x-intercepts if requested to do so. And sometimes to do this, you have to resort to using Newton-Raphson's method and finding the x-intercepts using approximation. In our first example, we've been asked to sketch this polynomial f of x, which is x to the 4 minus 4x cubed plus 1. We're going to start, and I tend to start this way every time, by finding the stationary points. The stationary points are when your derivative is equal to 0. In other words, I'm going to try and find out what is f prime x equals 0. That will be 4x cubed minus 12x squared is equal to 0. In other words, if I factorize now, I'm going to get 4x squared and then x minus 3 is equal to 0, which means that I could possibly have a stationary point when x is equal to 0 or when x is equal to 3. If I substitute 0 into f of x, I find that f at 0 is equal to 1. This is actually going to be a y-intercept. If I substitute 3 into f of x, I find that f at 3, the y value when x is 3, gives me an answer of minus 26. Now I can see straight away that I have two possible stationary points. What I'm going to do next is I'm going to check and see whether they are local maximum or local minimum stationary points. Remember, when I want to test whether my stationary point is a local maximum or a local minimum, I must find the second derivative. So I'm going to find f dash dash x. And this is going to be 12x squared minus 24x. Now what I'm going to do is I'm going to take my x value, the first x value was 0, and I substitute that into the second derivative. And when I do that, I actually get a 0. Now that means that the concavity changes when x is 0. I'm going to check that just now by using my concavity testing table. For the second one, when I put in when x is 3, I get an answer of 36. Now 36 is a positive number, and if I test and I get a positive number, it means that when x is 3 and y is minus 26, I'm going to have a minimum turning point. So I already have some important information about my stationary points. As I found when x was 0 that the second derivative was 0, I'm now going to check and see what is my concavity around when x is 0. So as we saw, when x was 0, the second derivative was 0. I'm going to test a number just smaller than 0. An obvious number to test is when x is minus 1. I'm also going to test a number just bigger than 0. And for that, I'm going to choose 1. Now for the first answer, I find the second derivative when x is minus 1. And my answer is going to be a positive number. Now when I put x as 1 into the second derivative, I get a negative answer. In other words, I'm going to find that my graph is going to be concave up, and then it inflects when x is 0, and then it's going to be concave down. If I take a look at the sketch that I've given you over here, let's try and confirm the information that we've already managed to achieve, to find. So we said that our y-intercept was going to be at 0, 1. This is when x is 0. We said to the left of it, our graph was going to be concave up, and then to the right of when x is 0, our graph was concave down. We also said that we would have a turning point, which is a stationary point, when x was equal to 3 and when y was minus 26. And we also discovered, lastly, that this stationary point was a local minimum stationary point. I now have basically got the shape of my graph. By just having this information that I've shown you in green, I could have just joined the lines dot to dot, and I would have managed to get the curve as shown by the red line. There's one more thing, though, that you might perhaps have wanted to find out, and that would have been your x-intercepts. Now, these x-intercepts would not have been easy for you to find unless you had resorted to using Newton-Raphson. What would you have used for your first approximation? Well, we know that when x was 0, I had positive y values, so that is over here. When x was 3, I had negative y values, so that was down here. In other words, my curve must have cut the x-axis somewhere between when x was 0 and when x was 3. So if I wanted to find this first x-intercept here, for my first approximation, I would choose 1, 5. Let's try the same thing for the second x-intercept, which is over here. All we know is that my graph is increasing after when x is 3. If you wanted to find an x-intercept, it had to be greater than 3. So for my second approximation, to find my next x-intercept, I would have chosen something just bigger than 3, and in this case, I'm going to choose 3, 1. See if you can do that using Newton-Raphson. If you've forgotten, go back to the other videos and check the method. Once you have finished, you'll find that you get two very nice x-intercepts. The first x-intercept over here is going to be 0,6696, rounded to 4 decimal places. And the x-intercept over here is going to be 3,9842, also rounded to 4 decimal places.